Hello everyone, this video will talk about systems that include dissipative force and how that affects the total mechanical energy. In the previous section we learned that when the non-conservative forces applied on a system is equal to zero, the total mechanical energy would be conserved, meaning that the total mechanical energy at any moment will be constant. Now when a non-conservative force like friction is present, the work done by non-conservative forces will not be zero anymore. It will be a negative work that dissipates energy. And in that case, the sum of the kinetic energy plus the sum of the potential energy will be equal to the work done by the friction in that system. And this friction will produce negative work, as you see here. Again, if we rearrange the equation, we'll see that the total mechanical energy initially is bigger than the total mechanical energy after certain time t, and that's because of the energy dissipated by the work done by the friction. Now we can go ahead and add our new equation to the list of equations that we have over work and energy related equations. This new equation is only limited to the presence of dissipative force as friction. Okay, let's go ahead and solve problem over that. So here you have the mass given and the initial speed of an object dropped from a cliff. So here will be the initial conditions and here will be the final condition. Now the initial velocity is given to be 1 to p15. And we have the displacement, which is 150 meters downward. Down. This is the velocity also down. And we are asked to find the final velocity. Also, we know the average air frictional force, which is given to be 10 Newton downward. Okay. Now we can solve this problem using Newton's second law to find the acceleration. And after we find the acceleration, we'll have three quantities: the initial velocity, the displacement, and the acceleration. So we can solve for the final velocity using equation number 5, the kinematic equation number 5. V final square equals V initial square plus 2 times the acceleration times the displacement. But this will be a long way to solve it. An easier way to solve it is to apply the equation that we derived for the work done by non-conservative forces, which will be equal to the change in the mechanical energy, which is basically the initial kinetic energy plus the initial potential energy, and the work done by the non-conservative force is the force of friction times the distance. This is equal to the final mechanical energy. We know that kinetic energy is 1/2 mv squared. The potential energy is the weight times the height. Now y final is 0, so this part here is 0 because y final is 0. Now we can go ahead and plug the numbers. 2.5 kilogram for the mass, 15 meters per second for the initial velocity, 150 meters for the initial height, 10 Newton for the friction, and 150 meters for the distance. This is the left-hand side of the equation, equal to the right-hand side, which only has the final kinetic energy. And the only unknown here is the final velocity. So now we solve for the final velocity. Now the initial kinetic energy will yield 281.25 joules. The initial potential energy will yield 3,675 joules. The work done by the friction, the dissipative force, this will yield 2,456.25 joules. And we try to delay rounding off till the end of the problem to get an accurate numbers. So this is the left hand side. This is equal to the right hand side, which is 1/2 times 2.5, which will yield 1.25 kilogram times the final velocity square. Now we solve for the final velocity square, and we take the square root. Now recall that joule is kilogram meter square over second square. and kilogram will cancel out with kilogram. And if you divide 2456.25 by 1.25, this will yield 1965, and this is meter square over second square. Taking the square root of 1965 will yield 44.3 meter per second, rounded off to 3 significant figures, and this is downward. Now, if you solve the problem using kinematics equations, you'll get the same answer. You apply the sum of the forces in the y direction equal to mass times acceleration. The net force will come out to be negative 14.5, which is the weight minus the friction, and this will be in the negative direction, equal to the mass times acceleration, and you solve for the acceleration. This will yield 5.8 meter per second square in the negative y direction, downward. And then you solve for the final velocity using equation number 5, and this will yield the same answer. Okay, this problem is composed of two parts. In the first part, where the box is sliding down the incline, the work done by non-conservative forces is 0, meaning this is a conservative system where the only force is related to gravity. So this is basically stage 1 of the problem. Then you enter stage 2 of the problem, where the box encountered a rough patch. Hence, the work done by non-conservative forces is no longer 0. It will be equal to the work done by the kinetic friction. In this problem, we are asked to find the velocity of the box when it slides off the 4-meter rough patch. It's the velocity at this point, which is related to stage 2 of the problem. Now let's go ahead and apply the work done by non-conservative forces is equal to the change in the kinetic energy plus the change in the potential energy, which is the change in the mechanical energy. And if we write it in its extended format, it's the initial kinetic energy plus the initial potential energy minus the work done by the friction is equal to the final kinetic energy plus the final potential energy. And this is stage 2. So we are trying to see if we can solve the problem directly by applying the equation of the work done on stage 2. Now let's go and plug the values. Now for stage 2, the initial condition will be here at the moment the box enters the rough patch area. This will be the initial. And the final condition is at the end of this rough patch. So this is the final condition. So the initial kinetic energy will be 1/2 times the mass, which is 15 kilogram, times the initial velocity, which we do not know. The initial velocity at which the box will enter the rough patch is not known to us. Plus the initial potential energy at this point. The initial potential energy is 0. There is no elevation. Minus the work done by the friction. And this one we can evaluate because we know friction is equal to the coefficient of friction. Let me write it here on the side. We call the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. And in this case here, on the flat surface, the normal force will be equal to the weight. Hence, the force of friction is equal to 0.59 times the mass, which is 15 kilogram, times 9.8 meter per second square, and this will yield 86.73 newtons. So now we can go back to our equation here. We stopped at that point here where the friction times distance is equal to the final kinetic energy plus the final potential energy, and the final potential energy will be 0 because again the elevation here is 0. So now we can complete 1/2 times 15 is 17.5 kilogram times the initial velocity square plus 0 minus the force of friction, Newton, times the distance, which is 4 meters, because the box moved 4 meters over the rough patch. This is equal to the right hand side, which is 1/2 the mass, times the final velocity square, and this is the unknown. The unknown is the final velocity square, plus the final potential energy, which is 0. So if you look at this equation, we have two unknowns. We have the initial velocity of the box when it enters the rough patch, and the final velocity, which is the unknown, which we are asked to solve for. So we cannot solve this equation, and hence we have to refer back to stage 1 in order to find the initial velocity of stage 2. This is because the final velocity of stage 1 is equal to the initial velocity of stage 2. Okay, so now in stage 1, the initial condition is here. That's when the box starts sliding, and the final condition is here. This is for stage 1. Also in stage 1, the mechanical energy is conserved because there are no non-conservative forces acting on the object. Hence, the initial kinetic energy plus the initial potential energy is equal to the initial kinetic energy plus the final kinetic energy. And now we can go ahead and apply the formulas and at the same time plug the numbers for stage 1. The initial kinetic energy is 0, where the box was dropped from rest, and the initial potential energy is the weight times the height, which is 6.5 meters. This is equal to the right hand side, which is the final kinetic energy, 1/2 the mass times the final velocity squared, plus the final potential energy, which is 0, because at the final point the elevation is 0. And now we have one unknown, which is the final velocity of stage 2. So we solve for the unknown. Note here that the 15 kilogram will cancel out on the two sides of the equation, as it is present on the two sides of the equation, and this will yield 127.4 meters square over second square. Taking the square root, we'll find the final velocity of stage 1, which is 11.29 meter per second. So now we can take this value and plug it into stage 2 equation. So replacing V initial of stage 2. So going back to stage 2 equation here. So now V initial square will be replaced by 127.4 meters square over second square plus 0 minus 86.73 times 4. And let me do a correction here. The 1/2 times the mass is 7.5 kilograms, since the mass is 15. Okay, so this will be 7.5 kilogram, this will be 7.5 kilogram. 86.73 times 4 meters should yield 346.92 joules. This is the left hand side of stage 2 equation. The right hand side of stage 2 equation will be 1/2 the mass, which is 7.5 kilogram, times the final velocity square. And now we solve for the final velocity, which is the unknown in the question. 7.5 times 127.4 will yield 955.5 joules. You subtract minus 346.92 joules will yield 608.58 joules. This is equal to the right hand side, which is 7.5 kilogram times the final velocity square. Rearrange the equation to solve for the final velocity square. This will yield 81.144 meters square over second square. Again, joule over kilogram will give you meters square over second square. Take the square root of both sides, and the final velocity would come out to be 9.01, rounded off to 3 significant figures. And this is moving to the left.